to say two personal things. What Eric is going to tell us is about three-dimensional pathways in the surface of the ocean. And actually this story, for me at least, started in 1988 actually, in the area that he's going to actually show the plans and the initial work that we're doing. And the area is the Eastern Almeria-Oran Sea. We started a very intense collaboration at that time with US scientists at that time, Bob Arnaud, Paul Laviolette, and many others, really somehow discovering a front, what is called now the Almeria-Oran Front, the eastern boundary of the Eastern Gyres, and really working intensively on vertical motions in the area. We have continued with this along the years, first with Damia Gomes here, Ananda, John Allen, Simon, etc., and all of us, Hano now later, now in the present time also with some intense numerical work by the SOCIB team, led by Baptiste. And I think we are extremely fortunate to have somebody like Eric. I was reading his papers when I was a PhD student at that time, so I think it is really great that after so many years we have really converged in this CALYPSO issue. Eric Dassaro is really, you all know him, leading scientist in this area, and I think the best is that we hear you, Eric, and we really thank you very much for being here, for leading all this, and for now your seminar. Thanks very much.
Yeah, I will be a little bit subdued, though you might not notice. I'm actually, besides being jet lagged, I'm also have a bad cold. And I will try to talk softly to preserve my voice, but hopefully that will work. So I was first here we go, a year ago, just about exactly a year ago, in a planning meeting for this program called CALYPSO. This is a U.S. Office of Naval Research, Accelerated Research Initiative. The way the Naval Office of Research works is they have these programs that last 5 years and they focus on one particular problem. And the person, Amala Mahadevan, there sort of initiated this contact, and we did a preliminary meeting about a year ago. And this is, they always have funny names, but the basic focus of this program is to look at vertical exchange, the exchange of particles and mass and other things from the surface into the upper ocean in a way that's cartooned in here. This is from a paper from the North Atlantic, but this is a phenomenon that happens all over the world, where you have productivity, as indicated by the green dots in the surface ocean, and it can mix down by regular turbulent mixing, and it can also mix down through the action of mesoscale and submesoscale eddies, as is indicated by this sort of swirling motion here. So the purpose of CALYPSO is to try to understand that better. It turns out that in the Western Mediterranean, in this region, is a particularly good place to look at this, both because there's a lot of historical data working on this problem in this region, and also because there's some very strong fronts, and fronts turn out to be the key part of this. There are also links to fancy theoretical things about Lagrangian coherent structures. So the basic idea is to try to measure and predict three-dimensional pathways of transport from the surface into the interior, to understand what that means for the exchange of heat, gas, and other things, and the fate of drifting objects. In order for water to sink, for surface water to sink, it has to come together and move downward. And if the material on the surface is floating, then it comes together just fine, but because it's floating, it doesn't sink and it accumulates. And so that's actually rather important. This has definitely got to focus on fronts, scales of kilometers, really quite small scales, because on large scales, the rotation of the Earth through geostrophy doesn't allow water to sink. So if you want it to sink, it has to happen on small enough scales that constraint doesn't occur. So we're going to be looking at quite small scales. And we'll talk about this in a moment. This is obviously partnering with you guys. I came here last year, and the whole US team was tremendously impressed by this set of institutes here. and how nicely you had been organized and how nicely you had focused your work, particularly on autonomous things, in what we thought was a very clever way to do things. So this will be focused on observations and modeling, but in particular observations today, particular focus on vertical velocity, which is one of the quantities that's hardest to measure in the ocean. I'll talk quite a bit about that. But what we have found over a decade or so of doing this is that it's the combination of different types of autonomous platforms along with ships that's the most powerful thing. We're talking about big ranges of scales, measuring from kilometers to maybe 100 kilometers if you can. And to cover all those range of space and time scales, you need lots of different tools. And I'll talk a little bit about that. So let me talk about maybe the simplest question you could ask. We're going to talk about vertical exchange. Well, if you want to have vertical exchange, you've got to have vertical velocity. And you might say, well, how big are vertical velocities? We've all been taught that they're very, very small. Well, we'll see. They certainly are hard to measure. Historically, they've been impossible to measure on the larger scales in the ocean, and so they are inferred indirectly. This is one approach which has been extremely active in this part of the world. Here's an example from a paper from here. So if we think of, there's Algeria, there's Spain. If you imagine one of the eddies in this meandering current that's coming from the Atlantic, here's one of them, meandering around like this. Simon did a bunch of fancy analysis which allowed him to look in this region. We don't have to talk about those details. And looking in depth now, you have Mediterranean water deep, Atlantic water shallow, and a front that separates the two of them. That comes up to the surface. And a hint that there is vertical exchange is shown here by a section of chlorophyll. So there's a subsurface chlorophyll maximum, which is very deeply depressed. It's depressed to 120 meters. There's no light at 120 meters, so it's not growing. The way you get chlorophyll down here is by moving this water down along these density surfaces. But the picture doesn't really tell you how fast it's moving down. You might guess that it didn't take a year because the chlorophyll wouldn't last a year. But exactly what it is, you don't know. So one way to do that, which is explored in this paper, is to use dynamical constraints, a thing called the omega equation, in which you can say, well, it's going down here and up here, and that's sort of right. In other words, it's up here, down here, and the number that was gotten in this paper was about a meter per day. That is 10 microns per second. I like MKS units. There's a long story about that, but I won't go into it. And the very important thing is that is on a horizontal scale of sort of 50 to 100 kilometers. Scale really matters in this question. But for example, John Allen, working in the same region, different days, different things, saw 20 meters per day using similar methods, but this was on a 10-kilometer scale. And one of the things I've been claiming is that that's partially just because of the smaller scale. The smaller scale you go to, the faster it appears to be, which is a little confusing, and I'm still confused. So that's one of the questions. Now, a key insight into this problem has come in the last decade through a large amount of numerical work, which has now gone under the fashionable name of submesoscale structures. Here's an example of a very high-resolution ROMS model from University of California in Los Angeles, Jim McWilliams' group. So things are a little twisted. This is North America. North is sort of that way. It's a model. You can turn it around any way you want. This is Cape Hatteras. This is temperature, and the Gulf Stream is coming here and separating from the coast at Cape Hatteras and zooming up like this. This is one of the Gulf Stream rings. So that's temperature, and mostly it's cold water, warm water, and there's a very sharp front between the two. The model has 500-meter resolution. The critical understanding was when you go from a model with, say, 10-kilometer or 5-kilometer resolution, you think everything's fine, and when you go to half a kilometer resolution, all of a sudden you get all sorts of small-scale stuff, which is the submesoscale, which is most nicely shown by a plot like this, which is vorticity, the spinning of the water. And you can see that basically these structures are all as small as they could be given the resolution of the model. In other words, they are a few kilometers in scale. If you were to plot vertical velocity, these stripes of vorticity spinning that way there would be also what velocity would look like. So what the models have revealed to us is that there are velocities of a few millimeters a second, is what the models say, which is 10 to the minus 3 meters per second as opposed to 10 to the minus 5 meters a second. So that a millimeter per second is 100 meters a day. Okay, so the key new idea is that there's a lot of very small-scale texture to the ocean, which is due to a whole set of structures and a whole set of new dynamics which can have large vertical velocities. That's the key new idea that's come from models. We've tried, we is sort of a big we, myself, my group, and many other people in a number of programs over the last decade or so to try to make observations that ask whether or not these things are really there. And one which I'm about to show you was done in the Gulf of Mexico in the United States, putting out very large numbers of surface drifters, satellite drifters that are tracked on scales that are sort of, like that. So you would see all those little wiggles. So the next thing I'm going to show you is a little movie of drifters. See if that works. So that's the ship, and it's putting out drifters. The dots are the drifters. That's 5 kilometers. The drifters are all swirling around. The ship goes home. It's very much like the SOCIB ship, actually. You can see they had to go home because the weather got bad. You can see there's you noticed that, right? You can see that now the wind is blowing now, which is why we had to go home, and it's not interesting things. But now, as the wind lets up, these drifters start to form some really interesting patterns. These are surface drifters. It's all 2D, again, on scales of 5 kilometers. So here you can see there's this is a strong convergence. The drifters are all going into this region. We get to come back. And then we start surveying. Notice that the drifters are caught in this about 2 or 3 kilometer wide eddy, and they're swirling round and round with some funny little structures that occur. So then the ship comes, and then we ran out of time. You know about that too. But you see, we did some really beautiful little surveys, and then we had to go home. And then the movie stops. Right, okay. That sort of gives you a general idea. So the thing you get from that movie is indeed there are a lot of small-scale things that occur in the ocean, like you saw in the previous slide, which if I show, I'll have to show the movie again. And we need to think a little bit more about those. So here's another version of that same data from just the first part, which gives you sort of a feeling about how dynamic the small scales of the ocean can be. There we are putting out the drifters, and I've colored the drifter lines. There we go. Okay, by density, the density at the time that the drifter was put out, and you can see this is a day of data, and you can see in a day how much small-scale strain and how much all sorts of eddies that are like a few kilometers across that are stirring this all up. So this definitely happens. And what? Yeah. Well, the gradients are big. The density range is pretty small. That's 0.2. Well, 0.2. See, there's. Yes. Well, yes, that's right. So the stronger the density. Yes. Well, that's right. But okay. I'll spin Ananda's comment. She says, well, in this place where all sorts of interesting things happen, the density gradients are quite small. And in the Mediterranean, where the density gradients are bigger, it should be even better. Yeah. How about that? But the important point is, I'm glossing over all sorts of details. The way the physics of these sort of motions works is you have density gradients in the ocean, heavy water somewhere, lighter water somewhere else. The mesoscale eddies bring those together in fronts, And that density contrast is what's powering these motions. At least that's what the models say. This is basically a baroclinic instability that's happening on small scales and much faster than your usual larger instability. So the larger the density gradients, the more energetic this should be. It also depends a lot on the mixed layer depth. Deeper mixed layer depths are better, which means it's a big seasonal cycle, and if in the wintertime, it tends to be stronger. Okay, now, I got to go back and set this up. Okay, so a little later on in this particular experiment, the drifters gathered into this front, and then they swirled around. This is a detail of that. And certain drifters have been colored orange for reasons you're about to see. So here we go. So all these drifters are gathering into a front, and they're swirling. And you notice that the size of this is going from maybe 10 kilometers, now maybe it's 5 kilometers in size, and now it's getting even smaller. Maybe it's about 1.5 kilometers, and it keeps going and keeps going. And okay, see that? We went from, I can't stop it. Oh, I wish I knew how to stop it. There's a pattern here where drifters are at about 25 kilometers, the size of a city. And after about 3 or 4 days of activity, all the drifters have been gathered into a dot which you can't see. It's about 60 kilometers in size. In other words, 60 kilometers, 60 meters. It's as if everybody in the city went to the football stadium. Okay, so in order for surface water to gather together, it has to go down. But there's lots and lots of convergence in this picture. And so the next slide shows you additional evidence that there really is convergence and downwelling associated with these features. You remember that the ship was doing surveys. This map here is, now we're talking about 10 kilometers by 10 kilometers. And the drifters are swirling around. And the ship is going back and forth like that, and that's a map. Kilometer resolution. So you have, in this particular case, you have light water here, heavy water here. Along that yellow line, you have heavy water here, you have light water here, and a sloping front, a very generic, and then that's 1 kilometer. So we're talking very small scales. And what we did was we took one of these devices, which is about the size of me or you, and it's a device that I build, which is called the Lagrangian float, and it's a float like an Argo float, but actually built rather differently in a way that it can actually follow vertical velocities. So we put it in here, right next to the front. Why did we put it there? Because we had this survey and we knew there was a front there, which is why we didn't do it till the very end. And it followed along like this at the surface, or followed along like here at the surface, moving into the heavy side of the front. And then it went down, following these isopycnals like that, and then ended up here. And we didn't really have very good tracking, so we don't know really quite what it did once it was subsurface. Depth versus time, it started at the surface, and then it came up over here. Now how would you know this thing was actually following the water? You know, maybe it just went up and down because first of all, when it's going down, it's on the same isopycnal. It doesn't have to do that. So that it's got the same density. More important, new ADCP on the float. ADCP measures the velocity relative to the float. And the ADCP basically measured hardly any velocity. There's some subtleties I'm not going to talk about. But you can convert to what's the velocity of the water above the float. It's the velocity measured by the ADCP plus the velocity of the float. And if you plot that out, it's a couple centimeters a second here, or a couple thousand meters per day. It's also the rate that the float is sinking. So you have two independent measurements of the fact that the water is going down is going down at several centimeters a second in a region that is, we don't really know, but maybe a kilometer, maybe 100 meters. Well, the float is about 1 meter wide, so it's at least that wide. And the beams that are coming off spread out to maybe 50 meters or something like that. So some sort of small scale, we don't know what that scale is. So the point of this all is that, and this is way, way bigger than previous numbers, probably because the scale is smaller. In other words, if you go back, I'm going to make a mistake here, I know. If you go back to this picture says that there are lots of very small scale velocities, small scale structures, and these small scale structures have small scale velocities. Exactly how you hook up these small velocities with these, we don't know. That's part of the puzzle that we haven't. Okay, so what are we going to do? About a month from now, we have the first cruise of CALYPSO. Going to be on the Oran Front, right in here. Of the SOCIB, and also out of La Spezia. The main reason for this trip was to go check out this ship because I've never seen it before. Looks like it will work. And this is a pilot experiment. We get 1 week to figure this out. We'll have spent more than 1 week going on this trip, so it's a short cruise. And there's a number of questions we're going to ask. How big, are there big vertical velocities? Where are they? When are they? What do they do? How do we find them? We're just going to try to figure out what's going on. And here's a very rough idea of what we're going to be doing. So this is output from the SOCIB ROMS model as of 9 days ago that I happen to have. Obviously, here's Almeria, here's Algeria, we're up there, and meandering Almeria Sea current. That's the arrows. That's about 1 meter a second current. The color is salinity. So there's the fresher Atlantic water. This is the only place considered fresh. Every place else in the world, Atlantic water is the salty water. And the Med is not connected to the Red Sea. If it were, the Med would be the fresh water if it was the Red Sea. Maybe there's a little tiny bit about canal. Anybody know which way the Suez Canal flows? Does it go toward the Mediterranean or toward the Red Sea? Anybody know? I don't know. It couldn't be. Maybe they stop it with some sort of dams or something. Anyway. We have fresh, salty water here, fresh water here, and a very strong front here in the model and also in reality. This is the region we're going to focus on. That will be our port. And you can see there's some fine scale structure here. And what we are hoping for is that right in this region here where this water and this water come together to form a front, that they will be sinking, and that water parcels from this region, a mixture of this water and this water, will sink and go down some path like that, a little bit under the fresh water. Why do we think that? Well, it's this story here. Water at the front sinks underneath and goes underneath the front on the fresh side. After all, if it went that way, it would be unstable. And it can't go that way because it's stratified, so it has to go that way. That's the idea to look at. To do this is not so easy. It's really good that we have two vessels. And here's sort of a very rough sketch of what we're going to do. We're going to have 2 ships, the SOCIB and the Alliance, both with ADCP and some sort of towed instrument. Things happen so fast that an instrument that's towed from the ship and can profile fast is really the only way you can get CTD sections that are sort of this dense. This was done with an MVP, which is basically a little winch with a really heavy weight and a CTD on it that's winched up and down. There's several varieties of such instruments. We're trying to get both the measure both the water that moves down here and look at the little details, get vorticity and things like that along the front. So we're going to have, and we'll have 2 gliders, something like 80 drifters, a few floats. The idea is to do sort of one section here continuously, have some gliders that go around like this, put out a lot of drifters here, watch them drift off in this direction, try to follow them with the ship so that as the drifters, to get pictures that are like, this sort of idea. And we will see what happens. We get a week. You can't do that much in a week. That's the basic idea. That's what's going to happen. That was what I had to say.
Thanks very much, Eric. And we have time for some questions from anybody. Come on.
I like questions.
I'll start then. No, I think it'd be good if you can comment a little more on the difference on the vertical velocities that you showed from the large scale, the mesoscale, and the submesoscale. Maybe you can mention why or you can stress the relevance of that.
I have a wonderful slide about that. Let me see if I can find that. Oh man, it's so hard.
Basically, I can help you. I'll start.
You start.
One of the things that we were working and in the last years with Antonio Tovar and with in our interaction with some of our biologist friends, they could not really believe that there was going to be any almost any difference in doing stations such closure. Actually, this is a comment that Antonio made to us, and in particular to Ananda, in preparation of, was it Irene Cruz, Ananda? Algorex, sorry, Algorex in perceptions. And I think it's very relevant. What we are seeing with the new tools is that there is a huge variability, not only on the physics, but also in the biology, at the submesoscale, at the very small scale.
So this is a talk I gave at Ocean Sciences. How big are vertical velocities? Okay, you saw that slide. Is 1 centimeter a second a big vertical velocity? No, this won't take long. Okay. If you look at geological timescales, sea level goes up and down at about 10 femtometers per second. I just wanted to use the word femtometer per second. And nobody else has ever done that. Sea level rise in recent decades is about 10 nanometers a second. If you do inverse modeling on the mesoscale, you find vertical velocities that are about 10 microns a second. If you do omega equation, like we just saw, you get 100 microns per second. If you do submesoscale instabilities, you get 1 millimeter a second. Internal waves have 1 centimeter a second. Boundary layer turbulence have 1 centimeter a second. Huge, big internal waves have 1 meter a second. Plot all those things on a plot of horizontal scale versus vertical velocity. Crudely done. I just did this, what's called, Google science, right? Okay, there you go. There's 1 centimeter a second, 1 kilometer a day. Lots of small-scale stuff has that value. This is a factor of 10 to the 6th. It's a factor of 1 million. See, but let me explain. This is a very important difference. I have not lost my voice yet. If you think about horizontal, something we're very used to thinking about it, or temperature. If you go out and you put a thermometer in the water, the thermometer is measuring the temperature on that scale. And say it's 25 degrees Celsius. Okay? If you do a satellite image of the face, you might get 24.9, even though the sun is a kilometer. And if you go to a 10-kilometer footprint, it's pretty much the same. And it's not until you get to hundreds of thousands of temperature changes. Same thing with velocity. If you measure, your current meter measures velocity on that scale. On the other hand, the current that you measure from altimetry, which is on scales of a couple hundred kilometers, is pretty much the same. It's not perfect. And that's because for velocity and temperature, the big scales are dominant. Most of the variability is on big scales. Therefore, it doesn't matter if on a centimeter or a kilometer or 10 kilometers, it's more or less the same. Vertical velocity and temperature gradient and vorticity, those are all things that are primarily dominated by the small scales. So if you measure on, what's the, we think that the vorticity of 10 times f, that means something that rotates 10 times a day, more or less, except for the factor of 2, is a big vorticity. If you put something in the ocean with like little veins on it that's this big and ask how fast it rotates on average, it's 1 RPM. So, just throw something in your local water and watch, does it spin around? Yeah, once a minute, once every 2 or 3 minutes, not 2 hours. So, because vorticity and gradient, we're very used to thinking about things, to use more technical terms, we're used to thinking of things with red spectra. Vertical velocity has a white spectrum. A white spectrum says all the energy is at the smallest scale that you resolved. So if you go to smaller scale, the signal to noise get bigger. We're used to the idea that you measure, if your signal to noise is poor, you go to larger scale so you can average more. But if all the wiggles are on small scales, as you average more, you average away the signal too. So you have to sort of think about it in a different way. And we don't know really what happened, we don't really know what happens, sort of going over here and, somehow it comes down again or something, because if you go to small enough scale, and we don't really understand that cutoff. That's one of the frontiers in dynamical oceanography, because it's a hard range to measure, internal waves are mixed into it, and there's not enough resolution in models to span. The key tool in models that got you to, well, I don't have the slide anymore, got you to the that submesoscale was things like nested ROMs, where you could have big scale, where you could have of several thousand, and that could allow you to do those models. That was a long answer. Go. But someone else must have a question.
Yes. Do you have a guess of the magnitude of vertical velocities that we can get now in this pilot experiment for CALYPSO?
I think you'll see centimeters a second, but we will find out.
Yeah, it's like we have gradients of about 10 times. Or
there's
the
no
density there isn't a linear relationship between the density gradients and the vertical velocity.
That's a really good question, and I don't know the answer. In other words, if one thing you can see in this picture is if you go to vertical velocities much bigger than a centimeter a second, it tends to be non-hydrostatic, and that's a very severe situation. So you might, but I suspect you won't see or 10 centimeters a second, because I think there's some limit there of non-hydrostaticity, which makes things really different. But I don't really know that. So I'm hoping we'll see it. We'll find out. It's again, I don't have the slide I had before is gone. But try doing this. Call it a dozen times. Half the time you put it in the wrong place, or it doesn't work, and you only get a week. We'll learn something.
Thanks, Eric. Just a quick question about your Lagrangian floats. Mm-hmm. Technical question, so I'm giving up science for a minute. The floats are quite clearly made to be isopycnal.
No. They have a program. They can adjust their density any way they'd like. Okay?
Yes.
So that's the key idea. And they measure temperature and salinity twice, but that's a detail. So, and the equation of state of seawater. So measuring temperature and salinity, you know the density of seawater. We also work hard to understand the equation of state of the float, so that knowing the pressure and the temperature, we know the density. Given that, and the ability to adjust the density of the float to more accurately than you need, you can make them isopycnal, like a parcel of water that had that temperature and salinity, or you can make them Lagrangian, which means that they have the same density as the water that you measure. So I know exactly the question you're asking, but I'll draw the picture on, and it would take me a moment. So you have a front like this. Horrible picture, my apologies. Okay, it's convergent, probably more convergent on the light side, and so water is doing that with a little bit of. What we have seen now, a small enough number of times that we think we know the answer. You see, there's a subtlety there. Is that you put a float here, it converges as it converges to the front water, and its density is changing slightly, and the float compensate for that. So we measure the density, we keep on adjusting it, and then when it gets to the front, it gets carried down. So that's an intrinsically unstable situation, because if I'm in the water and I'm isopycnal, meaning I'm following an isopycnal, if I get pushed down, I make a mistake, so I'm a little bit too heavy, I will just say, oh, now I'm here, and I adjust myself to that water, and I can just tunnel through the ocean. So it's very tricky to do. We sometimes less than Lagrangian to stabilize it. But basically, it is fully Lagrangian, or there are isopycnal Lagrangian modes where we mix the two as a function of time scale.
I think that's what I was getting at.
Yes.
That's the really tricky bit is in the limit when the isopycnals are going vertical.
Yes.
That surely is the bit where the Lagrangian float and how it responds has the greatest noise in terms
Yes.
of are you measuring the vertical?
Yes, and so that's why we have seen things like this for many years. In fact, we have a student now who's looking at an old data set. But the fact that at the same time as that, you basically have the new generation of ADCPs that measure the velocity of the water relative to you gives you a great deal more confidence that you know what you're doing.
Sure.
That's really has been the key, and which is why I'm on this big kick about vertical velocity, because we now have a tool.
Thanks, Eric. Anybody else?
Somebody other than the big shots must have a question. Oh, well.
Thanks a lot.
Okay.
Thank you. Thanks, everybody. Thank you very much.
Yes.